Magnification in lenses. You know that convex lenses are mainly used for getting the enlarged images of the objects. These lenses are used by jewel makers, dentists, etc. Concave lenses are used for getting the diminished image of a larger area. These lenses are used in peepholes of doors. While designing the lens, we need to know what is the size and position of the images produced by it. In this session, we will learn about magnification and the factors affecting magnification in spherical lens. In order to understand magnification, we need to first understand a few definitions. Object distance, U. The distance of the object from the optical center is called the object distance. Image distance, V. The distance of the image from the optical center is called the image distance. Focal length, F. The distance of the principal focus from the optical center is called the focal length. Now let's see the formulae for image distance and height. The formula, which gives the relationship between the object distance U, the image distance V, and the focal length F of a lens is called the lens formula. 1 by V minus 1 by U equals 1 by F. Magnification is given by the ratio of the height of the image to the height of the object. It is expressed by the letter M. M equals H dash by H. Magnification is also expressed by the ratio of image distance to that of object distance. M equals V by U. To understand the image formation in lenses, the following sign conventions are used. The object is always placed to the left of the lens. That is, light from the object falls on the lens from the left-hand side. All distances parallel to the principal axis are measured from the optical center of the lens. All distances measured to the right of the optical center are taken as positive, and the distances measured to the left are taken as negative. Distances measured perpendicular to and above the principal axis are taken as positive. Distances measured perpendicular to and below the principal axis are taken as negative. Focal length of a convex lens is taken as positive. Focal length of a concave lens is taken as negative. Let us take an object of height 2 cm which is placed perpendicular to the principal axis, 15 cm away from a converging convex lens of focal length 10 cm. As per the formula, 1 by F equals 1 by U minus 1 by V. V equals 30 cm. The size of the image formed can be determined by the magnification formula, which is M equals H dash by H equals V by U. H dash equals H into V by U. Height of the image H dash is H dash equals minus 4 centimeters. M equals V by U equals minus 2 centimeters. The negative sign shows that the image is inverted and real. The image is 4 centimeters tall, which is formed at a distance of 30 centimeters on the other side of the lens. The image is 2 times enlarged. To understand the image formation in lens, let us now keep focal length a constant and vary the object distance U. Let's see what will happen to the image distance V, magnification M, and the height of the object H dash. Now we will keep object distance U a constant and change the focal length and see the subsequent changes to the image distance, magnification, and the height of the object. Now, let us take a concave lens whose focal length is 15 centimeters. At what distance should the object from the lens be placed so that it forms an image at 10 centimeters from the lens? A concave lens always forms a virtual erect image on the same side of the object. As per the lens formula, 1 by V minus 1 by U equals 1 by F. U equals minus 30 centimeters. The object distance is 30 centimeters. The size of the image formed can be determined by the magnification formula, which is M equals V by U. M equals plus 0.33. The positive sign shows that the image is erect and virtual. The image is 1/3 of the size of the object. Let's now keep focal length a constant and vary the object distance U. Let's see what will happen to the image distance V, magnification M, and the height of the object H dash. Now we will keep object distance U a constant and change the focal length and see the subsequent changes to the image distance, magnification, and the height of the object. From this demonstration, we've understood the following formulae. Lens formula, 1 by V minus 1 by U equals 1 by F. Magnification in a lens, M equals H dash by H or V by U. Power of a lens. You must have used the zoom option in a camera. Look at these images. Here we can see a picture captured by a camera and another one captured after zooming in. Ability to zoom in and capture good images depends on the power of lens. We also hear the words power of lens when we speak of spectacles people wear. What does this mean? The ability of a lens to converge or to diverge the rays of light falling on it is depending on the power of a lens. Hence, the degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. Power of lens is defined as the reciprocal of its focal length. If F is the focal length of the lens, then the power P equals 1 by F. The power of a lens is dependent on the focal length of a lens. The SI unit of power is diopter. If focal length is expressed in meters, then power is expressed in diopter. It is represented by the letter D. 1 diopter is the power of a lens whose focal length is 1 meter. Power of a convex lens is positive and that of a concave lens is negative. To increase the magnification or sharpness of the images in optical instruments, lenses are combined. The net power P of the lenses placed in contact is given by the algebraic sum of the individual powers P1, P2, P3 as P equals P1 plus P2 plus P3 plus so on. Some examples are cameras, microscopes and telescopes. Let's take two convex lenses L1 and L2 of varying focal lengths. When a beam of light is passed through the lens L1, the rays get converged at a point. Let's measure this distance. We can see that the light rays converge at a distance of 10 centimeters. Hence, the focal length of this lens is 10 centimeters. Applying the formula, the power is 10D. Now, let's pass the beam of light through L2 and measure the distance to the point at which the light rays converge. The distance is 20 centimeters. Hence, the power of this lens is 5D. From this demonstration, we have understood the following formulae. P equals 1 by F. You have now understood the properties, image formation and magnification in lenses. You have also seen some uses of lenses. Can you list more real-life application of lenses?